When aircraft apprentice Frank Whittle invented the turbojet engine, he transformed the aviation industry. The jet engine led to a new generation of aircraft. Experimental planes smashed through the sound barrier, soaring to speeds of 2,200 miles per hour. Modern jet engines have to be precision engineered to withstand the stresses they operate under. To find out how they do it, we're going to one of the most famous names in jet engine manufacturing. This is the Rolls-Royce turbine blade manufacturer and test facility in Derby, England. Rolls-Royce is one of the largest manufacturers of jet engines in the world and is at the forefront of engine design. The principle behind all jet engines is to generate thrust by creating a high-speed exhaust. To do this, a series of fan blades at the front of the engine sucks in huge volumes of air. This air is then pressurized by a series of compressors before being released into the combustion chamber. In the combustion chamber, the air is mixed with fuel and ignited. The explosion of hot gases are fed via a turbine before blasting from the rear nozzle as a high-velocity jet. This jet of hot gas propels the plane forward. A modern jet engine is made up of thousands of component parts, and each one has to be absolutely perfect. There's one component in particular which is essential to producing a powerful engine, and that is the all-important turbine blade.
The turbine blade is absolutely essential to the engine. It's the part of the engine that delivers the thrust the engine needs to deliver to propel the aircraft.
Each turbine blade produces 10 times more power than a typical car engine, and they have to operate under incredible mechanical stress. Sitting behind the combustion chamber in the most pressurized part of the engine, they are exposed to temperatures approaching 2,500 degrees Fahrenheit. This high operating temperature and pressure is the reason why modern jet engines are more efficient than ever before. Making turbine blades strong enough to cope with this stress is a major challenge for Rolls-Royce. Each blade is first designed using a computer-aided design program, or CAD. To survive the intense operating conditions, the blade will need to be manufactured to extremely minute tolerances. So Rolls-Royce employs some very specialized techniques. The CAD design is first turned into a wax mold. This mold will be used to create a blade from a nickel-based superalloy. The mold will allow for a process known as single crystallization. Most metals are made up of numerous crystals, but by making the metal monocrystalline, it will cope with higher temperatures. These molded blades then move on to an automated production line in a temperature-controlled environment. The next job is to begin the delicate task of shaping the blades. This is done with the Makino grinder. It works on 5 different axes and takes its instructions straight from the CAD definition. This overcomes the inaccuracies of manual operation. To ensure it has cut the blade to the correct specification, it uses a CMM, or coordinate measuring machine. This can take readings from any angle, which can then be checked against the specification. Once operational, each turbine blade will have to withstand huge pressures, so they must ensure it stays firmly in place. Its root has to be ground down to give a fir tree shape. It is this special root shape which will anchor it in position inside the engine. To allow each turbine blade to self-cool while the turbine is running, tiny holes as small as 310 microns in diameter are made along the length of the blade. To make such small holes, they use hollow brass electrodes and a current of water to cut into the nickel alloy. When the engine runs, cool air will be passed through these perforations to prevent the blade from melting. These improvements in blade cooling technology have helped make more efficient, high-temperature engines possible. Every stage of this manufacturing process is carefully monitored by a computer, by a pair of human eyes, and finally, some clever fiber optics. But even after all this care, the finished components aren't ready to be fitted to an aircraft until they've been tested. Using a specially designed building with a cavity wall over 10 feet thick, every engine is tested to full thrust. This gives the engineers a complete profile of the engine's performance without ever leaving the ground. Today, they are testing a Trent 1000 engine.
3, 2, 1, go.
This fifth-generation engine delivers up to 75,000 pounds of thrust and will be used on the new Boeing 787.
The aircraft, I believe, is entering into service in 2008. It's aimed at the Beijing Olympics, so we have to get our engines ready for that moment, if not well before.
But they don't just test for reliability. Every year, there are over 10,000 bird strikes in the U.S. alone. So it's essential that the engine can cope with this and keep running. Only if the engine can remain operational will it gain its certification from both the European Aviation Safety Agency and Rolls-Royce. So, next time you're flying off to the Bahamas on vacation, jetting off on business to Denver, or simply looking up at the sky watching the tracers left behind by a jet engine, remember, it's a part no bigger than your hand keeping it in the sky.